Good morning viewers, welcome to my YouTube videos on high physics norms.
Hi, good morning students. Today I would like to discuss about the topic refraction of light. First of all, you have to know the definition of refraction of light. The definition is the deviation of a light ray from its path when it travels from one medium to another medium. The medium should be transparent medium. The medium will be transparent medium. So that is the basic definition of the refraction of the light. Now in this you have to know some basic concepts also, like velocity of light. So what is the velocity of light? So in general, velocity of light can be represented with the symbol of c, or in some cases v also. The value is around 3 into 10 power 8 meter per second, or you can say 3 lakh kilometer per second. That is the velocity of light. So basing on this, some questions will be asked. When the thunderbolt comes, which will comes first? For that the answer is, when the thunderbolt comes, first light will come and then sound will come. Why? Because velocity of light is 3 into 10 power 8 meter per second, whereas the velocity of sound is 340 meter per second, which is very less than that of light. That's why light will come first and then sound. So this is about the velocity of light. Okay. So velocity of light in vacuum also, air also, like this. The medium changes, automatically velocity of light changing. See here, another topic, another point here is refractive index. Refractive index. So it is also named as optical density, you can say. That is, refractive index represented by the symbol of mu, or in some cases, in some books they use n also. So this is about the refractive index mu. Now how can you define this refractive index? So it is the ratio of speed of light in vacuum. Speed of light in vacuum, C, to speed of light in any medium. So simply you can say that mu is equal to, mathematically you can write C by V. This is the formula. In general, mu for air will be around 1, whereas refractive index of water will be 1.33, whereas for glass will be 1.5 or 3 by 2, you can see. So diamond have full maximum refractive index, that is 2.4. So this is about the refractive index. Now you can write with respect to, say for example, one medium, that is medium 1, with respect to medium 2. This can be represented like this, 1 and 2. That is nothing but mu 1 by mu 2. In this way you can write. For doing the problem, it will be helpful to us. So this is about the refractive index. Now another formula which is important for the competitive point of view, that is Cauchy's formula, Cauchy. According to the Cauchy's formula, refractive index of the medium, that is mu of medium, is given by a plus b by lambda square plus c by lambda power 4 plus 1. Here lambda you can call it as wavelength of light, That means from this formula we can write like this: refractive index is inversely proportional to square of the wavelength. This is the formula for this. This is the catcher's formula. In some special cases they will use this. Next will be, if you consider this is the glass plate, this is a glass plate of thickness x, let us say. When the light is passing through this glass plate from here to here, the time taken to travel here is in t seconds, let us say. Then the question is, what is the refractive index of the glass is mu. Velocity of light as usual is c. Then the question is, what is the time taken to travel from one end to other end? So the formula is time taken to travel from one to other end. T is equal to, the formula is mu x by c. This is one of the important formula for competitive point of view. Now we discuss when the light ray is traveling from one medium to another medium, what happened. Basically we have two types of mediums, a denser medium and a rarer medium. So these mediums represent depending on their optical density. If the molecule is containing full of molecules, then we can say it is a denser medium. Say in general, rarer medium can be considered as air as the rarer medium, whereas glass and water, these are all considered as the denser mediums in general. So depending on the condition given in the question, you can use that one. So first here is when light traveling from you can say denser medium to rarer medium. So when light travel from denser to rarer medium, so these will be divided by 2. Say for example, this is the dividing, this is one medium, you can say this is a denser medium, let us say. This is another medium, this is a rarer medium, you can say. Here is the refractive index is let us say mu2, this is a rarer medium is mu1, let us say. When the light is traveling from denser medium to rarer medium. So in general, if the medium is not present, we know that light travels in the straight line, which is nothing but the rectilinear propagation of the light. Now, how can you get the angle of incidence and angle of refraction, whatever it may be? Now, by drawing a normal here, say here I am drawing a normal, which is perpendicular, you can say. This is normal. So from this normal to this you can call as angle of incidence. That means when the light ray is moving from denser medium to a rarer medium, what happened? In the without medium, it will go straight. If the medium is present, that too traveling from denser to rarer medium, it will be bend away from the normal. Actually, it will go in this way, but it will bend away from the normal like this. So how can you get the refraction angle? This you can call as angle of refraction R. So from this I can say that when the light ray is traveling from denser to rarer medium, it will, what happened? This is incident ray, you can call this is incident ray. This is a refracted ray. So this will be bend away from normal. We can say. Now you can apply the formula, that is we can say that Snell's law. According to that law, we can write here refractive index is, this is mu2 sine of I, which is equal to mu1, this is mu1 sine of R. That means we can write from this simply mu1 by mu2 is equal to sine I by sine R. This is the formula. This you can call as, which is constant always. This law you can call as the Snell's law. This law you can call as Snell's law. Okay, this is about the first point. when the light traveling from denser medium to rarer medium, it will be bend away from the normal. Here you can apply the formula here, which is Snell's law. Next, number 2 point, when light travel from rarer to denser medium, what happens? Same thing you can use. Here I am drawing a line which divides the two mediums. Again, this is a rarer medium, this is a denser medium. This is refractive index mu1, this is refractive index mu2. These two are separated lines. Now we can say that when the light ray is traveling from rarer to denser medium in this way, in this direction. Okay. Actually, without the medium, it will travel like this in a straight line. Okay. How can you get the angles? Simply by drawing the normals. Yeah. So this is the incident ray as usual. Incident ray. How will you get the angle? Simply normal and incident. This we can call it as the incident angle I. Now in the absence of this medium, it will go straight, but medium is present here, which is more dense. That's why it will bend towards the normal. Got it? It will bend towards the normal. This ray you can call it as the refracted ray. Okay, this angle is called the angle of refraction. Again, you can apply the same law here. From this law, you can write mu1 sine I is equal to mu2 sine R. Or simply you can write mu2 by mu1 is equal to sine I by sine R. This is about the Snell's law. Got it? This is about the case 1 and case 2. When the light ray traveling from denser to rarer medium, it will bend away from the normal. When the light ray traveling from rarer to denser medium, it will bend towards the normal. Now, if you consider a rectangular glass slab, so when light ray traveling through a glass slab, what happened? Okay. Now, this is a glass slab. Let us say this is a glass slab. Okay. So, let us say when the light rays glass slab whose refractive index is some mu2, you can say refractive index. Here is the air whose refractive index is mu1, let us say. This is a glass slab. Here this is also air whose refractive index is again mu1 only. Now let us say when the light ray is allowed to fall on the glass slab with some angle. So how much angle? How can you get the angle of incidence? Simply by drawing a normal here. This is a normal and one you can say. This is the angle of incidence represented by symbol of I, which we can say incident ray. So what happened? This is one medium, this is another medium. No? So we can say that this is the denser medium, this is the rarer medium. So already we know that when the light traveling from this is a rarer medium to the denser medium. What happened? When the light traveling from rarer medium to denser medium, what happened? It bends towards the normal. That means actual path will be like this. Actual path will be like this. But it will bend towards the normal. That means you can write here like this. Yeah. So this you can say this is the angle of refraction R. Now again, that means it will traveling from one medium to another medium. This is, you can say, rarer medium. This is denser medium. Now at this point, we can say that again it will come out from the glass slab into the air. That means now it is traveling from denser to rarer medium. So actually, what is the condition for this? When the light traveling from a rarer to denser medium, it will bend towards the normal. When it is traveling from denser to rarer medium, it will move away from the normal. Simply, how will you get the angle here? Simply by drawing the normal. So this is the angle of refraction. These two angles are proportional angles. That's why these two are same. Now here it will move, actually it will move like this. It will flow like this. But instead, when it is traveling from denser to rarer medium, it will move away from the normal. That means it will be like this. So in this direction. How will you? This you can call as the E, which is a angle of emergent. E stands for angle of emergent. Okay. Now if you observe these two, incident and emergent angle, if you observe these two, in the absence of the prism, it will be in the parallel lines like this. Let us say these are the parallel. Okay, this parallel lines, this distance you can call as the lateral displacement L. You can call it as the lateral displacement L. So lateral displacement L depends on I value, that is incident angle, and refractive index mu value, and thickness of this slab T, and also colors, different colors, and also different colors. So if I is more, mu is more, T is more, and L is also more, that means I more, T more, mu more, sorry, mu more, this L more, T more, L more. So that means if these are all more values, then we will get the more lateral displacement. Here if you observe among the colors, VIBGR colors, violet having, you can say that violet having a maximum deviation. That's why violet have more deviation. We can say that less wavelength, it will have lateral shift is more. So you have to remember this point. For violet color, more deviation, less wavelength, so lateral displacement is more. So this is about the rectangular glass. In this, our next topic is convex lens. Convex lens. So this convex lens is also known as converging lens. You can say that. Actually, we say that is this a lens is the combination of prisms. You can say. Say in general, if the convex lens, we are for the practical point of view, we are considering thin lens. This is the shape of the convex lens. See bulgy type. This bulgy type. What it will contain? It will contain the central point, which we can call as the center of curvature of this lens. You can use generally biconvex lens. So this is center of curvature C of the lens. What it will containing? So the line passing through the center of curvature, you can call it as the principal axis. You can call it as the principal axis. Principal axis. Okay. Now let us say if an object is present here, let us say point size object I am taking here. Whenever object falls on one side of the lens, it will having two lines, two rays, you can say. One ray, this is another ray. Okay. Say if it is an object, point size object, if you consider the rays which are near to the away from the marginal rays, which we can call as, these are called as the marginal rays. The rays which is near to the principal axis, which we can call as the paraxial rays. These we can call as paraxial rays. Okay, here marginal rays will more bend. That's why due to the marginal rays, image is formed nearby the lens. This is image due to the marginal lens. These are the peripheral rays. Paraxial rays. Due to this, image is formed far from the lens. This is due to the paraxial rays. So overall, for this object, the image is formed in between marginal and paraxial rays. This is the basic concept of the convex lens. Later, we can discuss some rules and regulations for forming of the image in case of a convex lens. Okay. Now, formation of images in case of a convex lens. For this, you have some rules. Initially, you have to know that if it is a convex lens, you can better to draw a line here, which is passing through the center of the lens, which we can call it as the principal axis. This central point you can call as the center of curvature C1. From this side, you can better to use this scale so that 2 centimeter here from this 11 number 12 and yeah, you can use this one. So from this center you can use this one. Yeah, 2 centimeter you can put a point here, again at 2 centimeter put another point here. Here also same thing. For 2 centimeter you can put a point here, 1 centimeter and 2 centimeter. Yeah, these are the 2 points I'm considering. Say this is a f2, focus number 2. This is double that of 1, 2f2. This is focus f1. This is double that of focus f1, 2f1. Here, these are the fixed conditions. First, rule number 1. As you know that when the light ray which is parallel to the principal axis, this you can call as the principal axis. When the light ray which is parallel to the principal axis, it will passes through the focus point. It will passes through the focus point. So this is the rule number 1. So what about the rule number 2? So rule number 2, when the light traveling through the center of curvature, you better use another one. Rule number 2. Again I am drawing the convex lens, thin convex lens. This is a line passing to the center. See, say approximately this is f2, this is 2f2, this is f1, this is 2f1. Now when the light ray is traveling from the center of curvature, it will be undeviated. This is the one. So rule number 2, when the light ray is traveling through the center of curvature of the convex lens, it will move in the straight line. That is, this is undeviated. You can say undeviated. Okay. So rule number 3, exactly opposite to that of rule number 1. Again, convex lens. This is the principal axis, center of curvature, f2 to f2, f1 to f1. So rule number 3 is when the light ray is traveling through the focus point f1, it will be refracted and this should be parallel to the principal axis. These are rays which are similar to that of concave mirror. Okay, These are the three important rules you have to learn for the formation of the images. You have to use any two rules for the obtaining the formulas. Here, formation of images in a convex lens. For this is as usual convex lens. This is the center of curvature of the lens. C, focus point f1, focus point 2f1, focus point f2, 2f2. Say these are the focus points f1 and f2. C is the center of the curvature. Now in the first case, we can put the object beyond 2f1. Say for example, here is an object. I am putting here an object. This is an object. Say named as arrow mark is the head. This is a tail. This is AB is an object. Now you can, for the formation of the images, you have to use at least two rules among the three rules. Now first rule, as you know, that when the light ray is traveling from parallel to the principal axis. Say this is the light ray which is parallel to the x-axis, let us say here, which will passing through the center of curvature, let us say focus f2. So this is passing through the focus. This is the first rule. And now the second rule is the light ray passing through the center of curvature. Okay, you can use this. This is the center of curvature line. So you can use this line. Yeah, not exactly correct. So we can use this line. Yes. Okay. Now this is second line. So these two rays will meet at this point, let us say. Now the image is formed here in between f2 and 2f1. This is image formation, which is in the reverse shape, that is a dash and a b dash. So we can say that position of the object is beyond 2f1. So beyond 2f1, that means, so let us say this is at the 2f1 point, this is beyond 2f1. So due to this, image is formed in between f2 and 2f2. Okay, now what are the characteristics of this image? So first thing is inverted image. Inverted means obviously they really meet. That means we can say the characteristics are a real image formation. So this image formation is in between b by w, f2 and 2f2. So the characteristics are real. Real means obviously it linked with the inverted image, and also size will be some decreased. That means we can say that diminished. So these are the characteristics of the image formation when the object is beyond 2f1. This is the condition number 1. Okay, next case number 2. Say here in number 2 case, now the object is at a point of 2f1. Again you can apply the same last two laws here. One ray which is parallel to the principal axis, which is passing through the focus point. Yes, focus point. Okay, like this. Another ray which is passing through the center of curvature of the lens, like this. Yes, so at this point, let us see. Okay, now this is the position of 2f2, you can say. Now the image is formed at this point, that is this point is 2f2 position. So 2f2, a dash, b dash, this is a and b. So if you observe, these two are of same size. Actually for the taking the readings, it will somewhat exactly not readings, just imagination readings only. So at 2f, object is at 2f, image is also formed at the 2f only. So these are all the same size, let us assume these are the same size. Okay, the as usual conditions are real, inverted, and same size. object size and image size are both are same. Okay. Now if you consider the objects is in between f1 and 2f1 object position. So what is the image formation? Say again I am taking the two light rays. One ray is parallel to the x-axis, which is passing through the focus point. Another is passing through the center of curvature like this. That means here the two rays will meet at this point. Now you can get the images at this point beyond 2f0. So this is the formation of the image. Yeah, A dash and P dash, A and P. So this is the formation that is beyond 2f. Beyond 2f2. Okay. So same characteristics, somewhat different. Yeah, a real, inverted as usual. This is a magnified image, you can say that. Magnified. So if you observe the cases, first will be diminished and same size and magnified and then dash expected. In this fourth case, if the object is exactly at f1 point, again you have to use two rules. One ray is passing parallel to the principal axis, which is passing through the refracted through the passing through f2. Another light ray which is passing to the center of curvature of the lens like this. That means these two rays obtain which are outcoming rays from the other side of the lens, which two are parallel rays. Here you can observe the parallel rays. Parallel rays can be obtained here. So the parallel rays in general they meet at the long distance, that say we can say if they meet at the infinite point. So finally the image formation is at infinity. So image will be formed at infinity. So infinity image will form, but what are the characteristics when they form into infinity? Same thing here. Infinity, that means real, inverted, magnified, and you can say that highly magnified image. Highly magnified will be formed. This is the case number 4. Now last case here, case number 5. Again I am considering the convex lens. Principal axis, center of curvature, f2 to f2, f1 to f1. So if the object is in between f and c, what happened? This is an object. Again as usual you have to use two rays here. One ray which is parallel to the x-axis, as we know that, which is passing through the focus f2. Another line which is passing through the center of curvature. So like this. That means these two are diverged lines. Diverged rays which they will never meet. For this explanation I am considering if you extend it back towards back side, then the image may be formed here like this. If you extend it back, that means better to draw final value. If you extend it back side, the image will be formed at this point, which is highly enlarged. That means beyond 2f1, you can say. So image is formed. So behind the object. Image is formed behind the object. So what are the properties of this one? This is actually not existing, actually not made, really they are not made. That's why you can say the final properties are virtual and erect. Erect, or you can say upright. Erect and magnified image is formed. Now this, if you remember this one, that means this convex lens can be used as the magnifying glass. That means simply we can say this convex lens is a simple microscope. Simple microscope, which is magnifying glass. Okay, this is about the image formation in the convex lens. Okay.